So let's have a look then at optimal decision making. So let's have a look at, in fact, at the Bellman equation, which is going to play a large role in a slightly different form actually in the rest of this course. So I'm again going back to this perpetuity, so the very easy thing that we started out with. So I have this perpetuity, so P forever, so once we make the investment T equals 0, price remains constant. And actually we knew what its value was, right? It was P over R. Let me just revisit this P over R a bit and see how we might be able to compute this. And then we look at the following derivation of that same P over R. So we know what it is, but let me just point out a way of computing this, which is actually might give us some insight. So what you notice, or what you have defined, that the value at T equals 0 is called V of P. So it depends on what price is, of course. And suppose now that we wait 1 year, and then we end up at T equals 1, and we look at what we still have in our hands. So at T equals 1, we get the first P, right? So what do we still have? Well, we still have the outlook to get all this whole stream of the red P's here that remain starting in T equals 2. So from somebody who sits in T equals 1, we have this number of this amount of money P, but we also have this remaining value V1 of P, but this remaining value for this observer in T equals 1 exactly has the same form as what we had before, right? So if I'm in period 1, what do I get? Well, I will get price in period 1 period from now, I get P 2 periods from now, I get P 3 periods from now. So the remaining value that I have, that I expect, the present value of those things, exactly has the same form as what we had starting in period 0. So the continuation value, in other words, that we will have in period 1 is exactly the same as the total value that we have in period 0. So can we do something with that? Well, I'm claiming yes. So let me actually do this on paper. So there we go to the paper. So we had this, so we're sitting in T equals 0, and we get all these cash flows. And T equals 1, T equals 2, all these P's, etc., all the way up till perpetuity, and we call those this present value is V of P. And now I'm claiming that this total value that I get as observed from T equals 0 should be the same as what I get in period 1, first coupon, if you wish, the first P that I get in period 1, discounted of course because I get it after 1 year, plus whatever is the remaining value that I get in period 1. And I just argued, well, from a period 1 point of view, what remains is again a perpetuity of cash flows P. So again, it's worth V of P, but I get this in period 1, so I have to discount this 1 time more. So my claim is the total value of all these cash flows will be the same as the value of the cash flow that I get in period 1, plus the continuation value of these cash flows, both discounted by 1 plus R, because I get those two in period 1 itself. So I'm claiming that this equation here must hold. So let's see what that means. And does this allow us perhaps to get some insight? Well, let's multiply this whole expression by 1 plus R. So it gives us 1 plus R times V over P should equal P plus V over P. And of course, 1 times V over P is just V over P. So those two are going to cancel. So this thing is going to cancel with this thing. Or in other words, what remains here is that R times V over P should equal P. Or in other words, V of P, this function of P, should equal P divided by R. No surprise in terms of that answer, because we knew that should be the result, but what should sort of tickle our interest is the way in which you derive this. So by looking at this value of today as the value of the cash that we get tomorrow plus the continuation value that we get tomorrow or next year. Okay, so let's get back to the slide then. So here we see that same computation. So what did we do here? We wrote this value of P, which presumably we wouldn't know this, so in this particular case we did, but suppose we don't know what this value is, but we observed, or we can write this value in terms of what we get tomorrow, plus the value that we get tomorrow, but discounted. And from that we could actually derive what this value is. So even if we do not know what this value is, we can plug it into this formula and compute what it is. So if you wish, we can, that's why I put this picture here. We can pull ourselves actually up here. That's what the Baron of Münchhausen, of course, did. Pull himself out of this the swamp here with his horse by his own hair. So even if you don't know what VP is, you can write down something in terms of VP and then solve this to get what actually the expression is. So that's sort of a miraculous way, I think, to compute stuff. We don't know what it is, but we know some equation for it, and from that equation we can actually compute what it is. So can we, this was an easy example, right? So we would like to generalize this. So this generalization is called basically the Bellman principle, or dynamic programming. So what we argued was that the value of a stream of cash flow, there was some V, which will depend on today's price, P of 0. But we argued, well, we might be able to write this, might be useful to write this as the present value of the first cash flow that we get, the P in period 1, discounted, 1 plus R, plus the present value of whatever remains in period 1, the continuation value, V1 of P1, again discounted. And now in our example, we observe that this continuation value is actually precisely the same in this case to the current value. It was from a period 1 observer, there's basically no difference. He still has the same perpetuity, but now as viewed from time t equals 1. And by plugging that in, by plugging that same v of p in this equation, we get an equation for this value function. So this is an example essentially of a Bellman equation. So let's look at one other example. This is a growing perpetuity. So perhaps you also know a formula for the growing perpetuity, but let's see whether we can actually derive this using this same Bellman principle, so this dynamic programming principle. So what do we have here? We start at t equals 0, where price might be equal to p, and we might make an investment, and doing that, we will get again a price in period 1, but now inflated by a growth factor g, so it increases a bit, 1 plus g times the price. And in period 2, we get 1 plus g squared times the price. Period 3, 1 plus g to the power 3 to the power price. So price is growing in an exponential fashion actually, with this factor 1 plus g every year. So can we again use this Bellman principle to figure out what the value of this growing perpetuity is? Well, let's try to do that. So what do we have to do? Present value of all these growing cash flows today, given that today's price is at level P, V of P, what is it? Well, it will be next year's cash flows. Well, next year the cash flow will go up by this growth factor G, so 1 plus G times today's price P, discounted, 1 plus R, plus the continuation value discounted, so again 1 divided by 1 plus R. So what is this continuation value? Again, this is a growing perpetuity, right? From the point of view of t equals 1, we still have a growing stream of cash flows growing at a growth rate g, but we start out at a slightly higher level already. So we start out actually not at p, but at p already once increased, so 1 plus g times p. So again, at t equals 1, this continuation value is again a growing perpetuity with the growth rate g. But now, the slight difference is it's not evaluated at p itself, and now it should be evaluated at P1, or in other words, at 1 plus G times P. It's slightly grown version of P. But for the rest, this function V, if we know it, the general function of a growing general value as a function of price of a growing perpetuity, if we know it here, we can plug it in here. If we know it here, we can plug it in with this price P1 instead of P0. So can we do that? So what would that lead to? Well, this would be the Bellman equation for this growing perpetuity. So the value today is the cash flow tomorrow plus the continuation value tomorrow, which again is the same formula for growing perpetuity, but now evaluated at this new price. So again, this is an equation for V, but we might call this, or we should call this, a functional equation, because it's an equation that governs the form of the function V as a function of P. So we do not want to find a single value, but we want to find a whole function, a function of P, which satisfies this equation. So the question becomes, how do we find a function that satisfies a functional equation? Well, might be some general rules, but one general rule is perhaps you can guess and try out what it is. So that's often a useful way of solving equations, guessing the right answer or almost the right answer, and then figuring out how we can make that guess work. So we are indeed going to make a guess, not of the exact form, but almost of the exact form, and our guess is going to be, well, this probably is going to be a linear function. So let's have a look at that again on the paper. So we have this Bellman equation for the growing perpetuity. So the Bellman equation here is Bellman equation. It looks like this V of P, so the value of this growing perpetuity V as a function of what today's price is, should equal 1 plus this growth rate times P discounted plus the discounted value of this same function V, but now evaluated at this increased price, the higher price, 1 plus G times P. And we're going to guess, or the fancy word for this is Ansatz, that's German of course. We make an Ansatz, we make a guess that this V of P is actually linear. So it's some alpha, if you don't know which alpha, some number times P. That's a linear function, right? So we want to figure out is there an appropriate alpha which might solve this? Well, let's try to plug this in. So I'm going to plug in that V of P is actually alpha times P. So that alpha times P for this V of P should be equal to 1 plus G divided by 1 plus R times P plus 1 over 1 plus R. And again, here I have the value function evaluated at 1 plus G times P. So what is the value function? What's alpha times what's in the bracket? So it should be alpha times 1 plus GP in this case. Can we solve this? Well, let's see whether we can. Well, let's again multiply out by 1 plus R. So we get 1 plus R times alpha P equals 1 plus G times P plus alpha times 1 plus G P. So let's collect the terms that have an alpha, because we want to know what our alpha is. That's the unknown that we have, we want to determine. So we get, taking this alpha times 1 plus G of P to the left hand side, subtracting it there, we get R minus G times alpha P, because these ones are going to cancel. Sorry, the one over here and this one over here are going to cancel, so we are left with this R minus G times P times alpha equals 1 plus G times P, or in other words, the alpha must be, well, of course, it's P cancels cancels out on both sides. Alpha must be 1 plus G divided by R minus G. So that's nice. So we have a solution here. So we have a solution which will be valid for any P, because this works for any P. Actually, P cancels out in this expression. So Vp is alpha, with this particular alpha, times P. So let's see this back again on the slide. So there we are, all is well. So here we solved it. So alpha times P is indeed 1 plus G times P divided by R minus G, as I just computed. So this is indeed the value of a growing perpetuity, and perhaps you've recognized this from your earlier finance courses. So a growing perpetuity, we can also value this using this Bellman principle, this Bellman equation. So now that's all good and well, but what we want to, of course, is to add uncertainty to this. So we need to be able to work with this also in the presence of some uncertainty. So if this price P1 is uncertain, what do we want to know? We want to know the expected continuation value, I should say, not just the continuation value that we know, because we don't know yet what the price tomorrow will be. So what's today's value? Well, today's value, V at P equals 0, is going to be the expectation of the discounted value of for tomorrow. So the expectation of tomorrow's price, P1, discounted by 1 plus R, and the expectation of the continuation value that we will have tomorrow, again discounted by 1 plus R. So if we're working with uncertain prices, we have to add here the expectation of what we see tomorrow. So for this growing perpetuity, actually the same thing, the same valuation will hold, because this price grows with G on average. So that will be the average growth rate if we introduce some uncertainty. And this is going to work for this particular case because this V of P is actually linear. So working with expectations in a linear environment is actually pretty easy. So this is an important equation, so that's why I actually put it in this particularly nice picture frame, I guess. So this is the Bellman equation once again. Bellman equation in discrete time, but under uncertainty. The value today depends on the price today, but the Bellman principle says, well, it should actually be equal to the expectation of tomorrow's price, tomorrow's cash flow, discounted, plus the continuation value at tomorrow's price, and again discounted by 1 plus R. So let's try to remember this. This is the Bellman equation, so it's important. And let's now add something to it, because so far we have just worked out what's the value of particular cash flow, but we want to add something. We want to add decisions to this. So we have been looking at investment decisions, and these decisions are going to impact on values. So we produced stuff that we already knew. So the power indeed of this Bellman equation is when we combine it now with these optimal decisions. So in this particular toy example that we looked at before, we just had essentially a simple decision. We only had to decide in period 0, do we want to invest now, or do we want to wait until period 1 when the H, the high scenario, materializes, or PL, the low scenario, materializes, and after that actually prices in this toy model remained constant. So what was the decision that we made? Well, we compare the value of investing today versus the value that we get if we wait a bit. So the value at t equals 0 was essentially the value of doing the best thing, and doing the best thing is taking the maximum of immediate investment, so in which case we get immediately the average P bar over R minus I, versus the expectation of waiting until tomorrow or until next year, in which case we would get V1, which might be either the high or the low V1, and again discounted. So you have this expectation over here. So this value is not just an expectation, but it's a maximum over the two different alternatives that you get. So in that case, we could solve this because we knew what this continuation value was, right? We knew what V1 was in both scenarios. So we knew that V1 in the high scenario was just this PH over R minus I, and V1 in the low scenario, particularly when this low price was low enough to make it not worthwhile to invest in that case was 0. So we could actually explicitly plug in that value in there and make that decision. So in general, we do not yet know, we don't know what this value is. We want to find it out. So the question remains, what do we do if we do not know this? So here's basically what would happen in that case. So in which case we would have this continuing uncertainty. So again, as we have looked at before, prices might go up or down. So I introduce this probability, I set it equal to 1/2 just to make life a bit easier. So with probability 1/2, price might go up in step 1, or with probability 1/2, it might go down with a shift delta. And then again in year 2, it might go up once again, or it might go down again back to its original level. And we have this whole tree. So if we do not invest right away at t equals 0, where we know price to be p, so will we then make this investment at t equals 1 when we know whether price is p plus delta or p minus delta? Or should we then wait a little bit longer? So you can imagine that you will make the investment when the price is high enough. So if price goes beyond some value, well, at some point you say, well, perhaps now is about time to make this investment, and if it's too low, well, perhaps now it's still time to wait. But you have to figure out, where is this optimal value p still? So again, here we are going to actually apply this Bellman principle. So here we are again going to observe that once we wait from period 1, period 0, so we do not invest in period 0, and we end up in period 1. Once we end up here in period 1, where are we? Well, we are again at some price level, p plus delta. Now we know that we are in the upper level here, p plus delta. And again, we have to figure out, what's the value of the project over here. Well, again, this whole red tree, so the remaining bit here, looks exactly like the black tree that we started out with, except it's shifted by this single shift delta upwards. So the value continuation value essentially that we have when we end up here should be precisely the same function as the value function that we would have here, but now evaluate, of course, at this high level p plus delta. Similarly, if we arrive at p minus delta, and the first time negative news, price has deteriorated a bit to p minus delta, again the continuation value that we have at this point, it's again this triangular tree, the red tree, the red part over here, which again looks exactly the same as our original black tree, but now shifted down to start at this beginning point, the starting point p minus delta, rather than at p which we had before. So we should see exactly the same value functions here, v, except that either it will be evaluated at p plus delta or at p minus delta. So also the decisions that we are going to make should be the same, of the same form at least. So the decision whether to invest or to wait should be of the same form as originally, except we make the decision at a new updated value of this price p. So what does it mean? So the price or the value of the project at the initial date, v of p, what should that be? Well, we make a decision today. So this decision today is we might make immediate investment, and on average this will give us p over r minus I, because on average the price will not move, because these probabilities were 1/2, if you remember. So that's what we get if we make the immediate investment. If we do not make the immediate investment, we'll wait. What do we get if we wait? Well, we get the average of the continuation values in the up scenario and the down scenarios, where these continuation values here again will include optimal decision making at the next date. So these V's over here actually include the decision whether, if I wait, whether I will make the investment at t equals 1 or whether I will again wait. from t equals 1 onwards. So what does that bring us? So this Bellman equation with investment will bring us that, or what we will do is we will want to today think about the maximum of the NPV of investing today, if we invest today, or getting the expected value of the value of this project tomorrow, including all the optimal decisions afterwards, discounted by 1+r, of course. So this V of P measures total value, but taking into account that in each stage we will make the optimal decision. So in stage 1, or stage at t equals 0, we will make the optimal decision. We choose the maximum here. Likewise, if we wait at t equals 1, we will again take the optimal decision. So this V over P tomorrow or next year again involves taking a maximum over, at that point, making the investment, or again waiting. So the question is going to be, can we find a function, some V of P, that solves that equality, including this maximization problem? So in this simple case that we looked at before, we could actually make this guess, but in this case, in this discrete time steps of 1 year each, that's not going to be so easy. To make our work a bit easier, so it sounds a bit more complicated at first, but in the end we can actually reach fairly simple expressions, fairly simple equations. We will have to go to continuous time. So instead of having discrete time steps, we'll just let time flow in a continuous manner. So that's what we'll do next week, actually, or next lecture, I should say. So let me just wrap up now for what we did today. So we figured out that you might invest to get some project, but sometimes it might actually pay to wait a bit, in particular when this P is moving up and down in an uncertain way. So this project itself is a real option. There's some decision that you might want to take based on what this uncertain price is doing, just like you might wait with exercising your call option until the stock price is high enough. And then the question was, how should we value that opportunity to invest? And we made some first steps at looking at the Bellman equation in this discrete time circumstances, and we figured out what you can write, or what we argued was basically, well, this value function must be a function which itself equals the maximum of either doing the investment today and getting the NPV today, or not doing the investment today. And well, what do we get in that case? Well, we get the continuation value, the expectation of the continuation value, V of P, tomorrow, including again the optimal decisions that will ensue once we have reached tomorrow. So on Thursday we will actually solve that equation. We're going to solve that equation in continuous time. In order to do so, we'll have a particular continuous time process for this P, and this process will be this geometric driving motion with a certain drift mu and a certain volatility sigma that we have looked at before. So I hope to see you in the next video.